Hello everyone, I'm Mighty, your hands-on practice assistant. In this session, we'll go through a CFD simulation together step by step and follow along with the practice example. The topic of today's practice example is radiation heat transfer analysis. What is a radiation heat transfer analysis? Radiation heat transfer analysis simulates the transfer of thermal energy through electromagnetic waves without material contact or fluid flow. Before we begin today's practice, let's check the model and boundary conditions. The analysis conditions for each region are shown on the screen. There is an inner chamber made of steel inside an outer chamber made of insulation material. 3 glass plates are placed inside the inner chamber and both chambers are filled with air. In this example, a compressible solver is required to account for the buoyancy effect caused by changes in air density and radiation effect. First, after running NFX, click New button in the upper left corner to create a project. Click Import in the Geometry tab to open the CAD file. Once the model is loaded, right-click in the workspace and select Hide All Guides. Now, let's move on to defining the material properties and analysis settings. For the air material, select the ideal gas material model. Now, we will create the materials for steel, glass, and insulation. For the insulation material, we will manually enter the material properties. Enter 300 for the mass density, 1000 for the specific heat, and 0.12 for the thermal conductivity, as shown on the screen. Then, right-click 3D, select CFD 3D, and create the material properties for each of the materials we just defined. Since NFX supports both structural analysis and CFD analysis, it is important to distinguish them carefully and select the correct options. Then, shall we generate the 3D mesh? Let's generate the 3D mesh as shown on the screen. Click the 3D tab, then first select the 3 glass plates and generate the mesh with an element size of 0.015 meters. Next, select the internal fluid domain and generate the mesh with an element size of 0.015 meters. For now, make sure to activate the Match Adjacent Faces and Merge Nodes checkboxes. These options are required to calculate fluid flow and heat transfer properly between each region, so please pay close attention to this step. Generate the mesh for each region as shown on the screen. After selecting all target regions for mesh generation, make sure that the properties have been correctly assigned. Click the arrow on the right and enable geometry proximity and avoid tetra with all boundary nodes to create a higher quality mesh. For the initial mesh generation, it is not necessary to enable the Match Adjacent Face Mesh and Merge Nodes options. However, for all subsequent mesh generations, these 2 options must be enabled. Please make sure not to overlook this requirement. Now, mesh generation is complete. Let's make sure the mesh is generated well inside the model by using Clipping Plane function. Let's define the boundary conditions as shown on the screen. Please follow the boundary condition setup process while watching the video. Also, check that the number of selected faces matches the screen as you proceed step by step. This time, activate only the internal air and external air models. Then, click Wall at the top and select all faces of the air domains. Check that a total of 36 faces are selected and then click OK. Next, click Flux at the top and select the 6 outer faces of the external air domain to apply the heat flux condition. Enter 10,000 for the heat flux. Now, we will define the most important boundary condition, the radiation condition. Click Cavity at the top to apply the cavity radiation condition. First, select the 6 outer faces of the external air domain. Enter an emissivity of 0.35 and max faces per surface of 10, then click Add. Next, select the 6 inner faces of the external air domain. Enter an emissivity of 0.35 and max faces per surface of 10, then click Add and OK. Now, select the 6 outer faces of the internal air domain. Enter an emissivity of 0.35 and max faces per surface of 10, then click Add. Next, select all 18 faces of the internal glass plates. Enter an emissivity of 0.8 and max faces per surface of 10, then click Add and OK. Now, the cavity radiation condition has been applied between the outer chamber and the inner chamber, and also between the inner chamber and the glass plates. Click Conduction at the top and select the 6 outer faces of the outer chamber to apply the conduction condition. Enter 25 for the ambient temperature and 10 for the conduction heat transfer coefficient. Now, we're almost done. Let's move on to creating and configuring the analysis case. For this radiation heat transfer analysis, all analysis modules must be enabled. Click Initial Condition, then select Field Definition, and set the initial temperature of both the fluid and solid domains to 300 degrees Celsius. If you right-click Analysis Case in the Analysis and Result tree on the left, you can see several predefined analysis types. From here, create a transient CFD, then click Edit. You will then see an analysis setup window like the one shown on the screen a moment ago. Configure the remaining settings as shown on the screen. Next, open the Module Data tab and enable Floatability by Density. Then, check the Absolute Temperature Scale option in the Parameter tab. Click Fluid Analysis of Analysis tab and increase the number of processors according to your computer specifications. The solver type must be set to pressure-based compressible. Before running the simulation, save the NFX file to your preferred location. Then, right-click the analysis case you created and select Solve to start the simulation. This analysis may take some time to complete, so we will skip ahead and review the intermediate results. For accurate results, the analysis should be run for a sufficient amount of time until the solution is fully converged, followed by a detailed review of the results. In the Analysis and Result tree on the left, you can review the results for each calculated step. Click the desired result item to activate the contour display. Let's check the temperature distribution on the clipping plane. Now, let's review the analysis results obtained from the simulation. While following along with today's practice, please make sure to remember these key points. How was today's lecture? Simulation may seem difficult at first, but if you follow the steps and practice hands-on, you can get started with confidence. With MIDAS NFX, learn the fundamentals one step at a time and challenge yourself with a variety of simulation examples. Then, see you again in the next video. This has been Mighty, your hands-on practice assistant.